Okay, now let's see this question. They are saying that G is an arbitrary group. Okay, any group is there where consider the following relations on G, and if A and B are elements of this group G, then they're talking about a relation R1 where A is in relation R1 with B if and only if there exists some G in this same group such that A and B are having relation among A and B and G are having relation between them. So for every A and B combination there must exist at least one G such that A is equal to G inverse B into G. If that happens, then A and B are in relation. And similarly that they have given another relation R2 where the condition is different, that for all A, B in this group G, A is in relation R2 with B if and only if they are inverse of each other. So A is equal to B inverse, then obviously you know it is a group, so B has to be inverse of A has to be inverse of B. In that sense, A and B, if they are inverse of each other, then only R2 holds, and they are asking about which of them is equivalence, these are equivalence relations. Okay, so we'll firstly figure out what is equivalence. Equivalence basically means three things you might already be knowing. First one is reflexive, second one is symmetric, third one is transitive. Okay, so if these are solved, these properties hold, then you can say that this is an equivalence relation. Okay, now I will start with relation R2 itself, because it on the face of only I can say that it is not equivalence, because it is not even reflexive. How can you say that every element for all A and B, every element is an inverse of itself? So in a group every element is inverse of itself. It is not always the case. There are some groups in which that is the case, but in general you cannot say that not itself even. So basically I am talking about just reflexive. So if A and A I am talking about, then A and R2, I don't know whether it is true or not, is in relation or not. So it can only happen when A is equal to A inverse, which means that every element is the inverse of itself, which is not always the case for all groups. So this thing is not also reflexive, does not hold, which means equivalence does not hold. It means R2 is not a equivalence relation. That problem is solved. We are only figuring out about R1 right now. Okay, that is a good question. We'll figure out. So R1 is, turns out that it is equivalence. So sorry for telling you in advance, but basically R1 is equivalence. We will step by step see that how it satisfies the property of reflexive, symmetric and transitive. Okay, let's take the first one. Okay, it is reflexive. See how. So R1 holds true if for all it means that we are talking about reflexive. So A should be in relation with A, and I am telling you it is true, but let's check it. Is A is in relation with? This can only happen if there exists some G such that A is equal to G inverse A G. Right, A is in relation with A, so instead of B I am putting A and this thing. Is there any element for this holds? That is simply the question. That is correct. Why? Because turns out if G is equal to the identity element, then you can write it as A is equal to identity element का inverse क्या होता है? It is again an identity element, right? So E into A into E, right? E inverse is E again. E into A is A, and A into E is again A is A, right? So turns out that it is reflexive. So reflexive property is satisfied. Let's come back to symmetric. If A is in relation with B, can we say that B is also in relation with same relation R1 with A? Can I say that? That is symmetric. Okay, so this thing is given. It means that A is equal to G inverse B, G. So they are saying that okay, there exists some G such that this thing holds, that thing is given to you. From that, can you deduce something like that? Turns out you can. Why? Because see, you can so let's say pre-multiply both of them by, let's so pre-multiply, let's say both of them by G. Okay, then it will become G into A, and then pre-multiply G, then G into G inverse will become identity element into B will become B and then G. Okay, then post multiply both of them by G inverse, then it is going to be G A G inverse, and this time post multiply G inverse, so identity into B is again. What I was trying to figure out, that A in terms of B it is there, I am trying to figure out B in terms of this thing. So turns out that I am getting something like B is equal to G into A into G inverse, but I have to have this format, G inverse into, so I can write it something like this. Okay, so I can write it something like G inverse is again G, right? A and G inverse. Now if you say G inverse is some other, let's say G prime, then you can write it like G primes inverse A into G prime. So there exists some element G prime for which this thing holds, right? First one's inverse into A into that thing again, right? That thing is following. So in that sense, definitely I can say that B is in relation with A, right? So B is in relation with A, that's true. So symmetric also turns out to be true. What about transitive? If this thing holds, then this is equivalence. Turns out it is transitive also. Let's see if you, how. So transitive means what? A is in relation with B, it's already given, and B is in relation with, same relation with C, that thing is also given. Can you say something like that A is in relation with C? Can you deduce something like that? Turns out you can. See how. If A is in relation with, then you know that it is something like, okay, A is equal to some G1 is some, it is there whose inverse into B into G1, right? Similarly, for B, you are having some B is equal to some G2, its inverse into C into G2, something like that will exist, right? If I replace this B by this entire expression, then what I'm getting? See, I'm getting G1 inverse, and then I'm putting this entire thing inside. Okay, so see what I'm getting G2 inverse C, and then I'm getting G2, this entire thing is B, and after B it was G1. Okay, so this thing I've got it. Okay, now I know that for any group, A B's whole inverse is equal to B inverse A inverse. This you might already be knowing, which means that I can write G1 inverse G2 inverse as G2 into G1 whole inverse. I can write that into C into G2 into G1. And if G2 is G1 is some, let's say H, then basically it is what? It is H inverse CH. Again it is coming in that format, right? That format. So there exists some H or G that in that sense, where this thing G inverse B into G holds, right? So B is so A is, you can see, is in direct relation with C. So this thing turns out to be true, and that's why it is transitive. All the three properties are satisfied. It means it is equivalence. It means that only R1. So B is R1 only. B is the correct answer.